Good morning, everyone. Can you hear me well? Just give me a thumbs up, please. Thank you. All right, great. So today we will go over mainly material for the midterm exam, but also wanted to go over a few updates to the Q&A. Let me go to the next slide. The Q&A session file that I shared with you. Reminder to reserve your midterm session ASAP. I'm looking at a bigger monitor because this one is full of the Zoom controls and other things. Uh, DSP students, I shared before, and it's also in the file that I'm gonna go over in a bit. I shared before that if you need accommodations that are not provided by CBTF, I did put a proctoring agreement in place with DSP. Please go ahead and book your exam with them. And it's for the entire week of the 16th. You can choose any day that is suitable for you and just go ahead and please reserve your test. I will send it to them before your exam. So do whatever is more comfortable for you. You're of course you're able to take it with CBTF. I did send all of your recommendations and they get updated daily. But if you feel that you need these accommodations that are not provided by CBTF, then please go ahead and book your exam with DSP directly. So let me go to the exam prep module, and then we will do uh, the rest of the tasks that we have for today. Okay, let me stop share first. You can send me if you don't want to. I don't share the chat, so you can send me questions on the chat. If you want to send me a direct message and like just message me and not the entire class, it's also okay. All right. Let me see what you're seeing. Okay, so yeah, that's the correct page. So there is a sample test that I sent. So if you look, these are all sorted by week. All the modules are sorted by week. Except for this module, it says midterm prep and info. So I tried to keep everything that is related to the midterm in this module. So please be aware that this module exists. I did send a few announcements about it. I did link it in one of the announcements, but just in case you missed that, everything will be in this module. So I put the sample test here. I will send out the answer keys. You requested that I expand the test, that I make it very similar to the midterm. I'm happy to do that. I will go over the slides probably today and send you some more questions. So I will update this test. I'll just add more questions to it. Does that sound good? And then I will share it with you by maybe tomorrow, today or tomorrow. Then there is the review session that we just was the Q&A session that we held before the midterm, like for the midterm. It was last week. It's also there. Oh, no, I need to go back. And then there is this updated file for that was discussed during that session, but I will go over this file because I made some changes. There's a question in the chat. I made some changes based on discussions with CBTF staff and with some of you. You requested a few things. If we've already taken it, we'll be able to take it again, the practice test. This one, yes. The one, so what happened is we were having a meeting and I requested that I be able to show you a few things that I this included in my announcement. Like, for example, what's the difference between invalid response and a wrong response, and a few things that I felt were important for you to know so that, we, like I said, we need to minimize as much as possible stress and unnecessary errors. I just want you to be, as relaxed as possible. You go into your exam, you're very well prepared. I think you'll be very well prepared. You have your study guide, you have your slides, you have all the lectures. Today, I will go over the slides and answer all of your questions. And because CBTF, this is the first time that we're trying it, so just wanted to make sure everything is well explained to you. So I requested that they do this again additional orientation quiz for you. Um, yeah, let me know if you have any issues taking it, but yes, you definitely can take it again. You, I think they allowed 1,000 sessions, and there is about 625 students, so it should be okay. I also added a study guide for you. So this was based on feedback that I got from students before. And so today is maybe tomorrow, I'll give you one more day. Today, maybe tomorrow by 5 p.m., send me any questions that you have related to the material, and I will update the study guide if there is anything that you would like to be like in a text form. Let me know. I will update it and I will announce, but I can't keep updating it because the exam is next week and I want people to like finish studying and like reviewing the study guide and not go back to it unless they need to. I will highlight any updated questions, or I will tell you in the announcement which questions have been updated. So you don't have to go over the entire study guide again. So there were two schools of thought. Number one, we organize it by lecture number, and then number two, we organize it by topic. But because we keep going back to topics as we learn more, so for example, we talked about subduction zones, like the first, second lecture very quickly, but we didn't really know what a subduction zone is. And then we keep coming back to that topic, and then we keep coming back to that topic again. So as much as we learn more, we discuss the same topic in different, different on different levels, let's say. So organized by topic one, the competition, and the study guide is organized by topic. So these are a few things that I think are important. We will go over the slides today as well. Some of you asked me whether they should learn all of the earthquake magnitudes that we learned. There are a few earthquakes that I expect you, sorry, dates that I expect you to know their dates and where they occurred, like the Kobe earthquake in Japan. I think I have Loma Prieta, of course, the 1906, San Francisco, Loma Prieta, also. There's one more. Yeah, the Parkfield earthquake from the Parkfield experiment discussed. I think I also I need to highlight the I just wanted you to know that there were some very large earthquakes in New Madrid between 1811 and 1812, but you don't need to know the exact magnitudes or anything. Just know that they existed, but they are in the study guide. I'll just highlight them as well. Yeah, so there isn't that many. We will have, as we know, we sprinkle case studies as we go because we need to accumulate knowledge for the study guide for the case studies to make sense. So I think now we are ready to discuss the Turkey earthquakes, and I did mention them very briefly when we were discussing the North Anatolian Fault, and I explained, how they are not on the North Anatolian Fault. Yeah, the 1906, and definitely the 1868 Hayward earthquake as well, because it's consequential for us, right? We talked about that a lot. So yeah, I did highlight them, and there will be more earthquakes, like we said, because there will be for the final exam study guide, I will be highlighting more earthquakes because we will be taking more case studies as we accumulate knowledge that will help us understand those case studies. But right now, I mean, these are sufficient for now. So just these. We will refer to them in the exam. We expect you just to know where they occurred, roughly how large doesn't, you don't, I won't ask you what the magnitude was, but roughly how large they were, like large or not. They're all damaging earthquakes, but some of them are significantly larger. And definitely need to probably also highlight the Tohoku earthquake, magnitude 9. So just to wrap this up, this is the study guide for you. Let me know if you need anything else added or if you have any feedback. I'm happy. I mean, the study guide was fully built on all through student feedback, so I'm happy to adjust it. The last version of that will be tomorrow. I'm not going to be able to adjust it further. So I'm going to, yeah, to just highlight more earthquakes that are included in the study guide, but I'm not going to update it beyond Friday so people have one stable version that they can work with and it doesn't keep changing. Any questions about that? We only have an hour and a half, unfortunately, so um, yes. Hopefully, I'll be able to answer all of your questions. Will anything not on the study guides come up on the exam? The study guide is not a transcript of the lectures. So possibly there is a disclaimer in the beginning. The study guide is intended as a supplementary resource. So it does not replace attending watching lectures. Okay, so yeah, it's to help you because lectures are, well, slides are better if they don't have much text on them. I do try to include text that I think need to be there, but most of the slides are just figures or photos, right? So that's not very helpful. Students, like I said, the best way to study for this course is to watch the lecture as if you will never see it again. Take very good notes, very good notes. Um, Try not to multitask, just watch and take notes. Don't watch while you're doing something else. You will not probably remember most of what you hear. So, yeah, I will get to readings. I'll get to that. I'll talk about it. Um, so yeah, take good notes and then you don't have to watch it again. Even if you need to, you look at the slides again and while you're reviewing and you see something that you're not sure about, at least you know where exactly to look and you don't have to watch a lot of videos to get to where you need to. Okay. So this is more of a supplement because my students in the past have asked me for it and they designed it themselves. They just they wanted it by topic because of the way we introduce a topic on like a low level and then we increase that level and we increase that level until we are we study something very deeply. So that's why it's organized by topic. And you will find that on the final exam study guide, there will be the same topic, but will maybe expand. So as we learn more, we're able to learn more. Okay? Any other questions? I'll get to that in a minute. All right, so that's for the study guide. And then there is this one. These are the slides that I shared with you last week. So it has everything you need to know about your midterm. Like I said, minimize stress. You have been already signing up. I see there is about maybe close to 80 students who haven't signed up yet. Maybe there are DSP students who are taking it with DSP, I'm not sure. But if you haven't already, please do sign up for your midterm. And we have I think we have from the 16th, almost the entire week, from the 16th to the 19th of March, multiple slots. And let us know if you have any issues with signing up. We're happy to help. I did go over this before, but I want to go over it again. But let me share my version of this, not because my version has the highlights, has the highlighted updates, so we don't have to go over the entire file again. All right, so this is what I shared with you last week. I did explain that if you have a true or false question on your test, and it has two statements. One of them is true and the other is false. That's false. It's an and, not an or. They both have to be correct. This statement, statement one and statement two. It's not statement one or statement two. It's an and, not an or. So remember, if you have even four statements, three are false, but one is true, that's false. Pick false. Okay? So some of you, I'm just warning you, I can't emphasize that enough. I've seen that happen in the past. Unfortunately, students read the first line and then they see something true that they click true and they go back and then they go to the next question. Please don't do that. Read the entire question. You have plenty of time. We gave you plenty of time for that. There's enough time to read all of the questions and think about them thoroughly. Make sure that you read it and so that if you see something, the first part of the statement or the question is correct, it's a correct statement, but then it's followed by an incorrect statement that you're able to um, click false. Okay. Let me know if you have any questions about that. The second one that I added, which is an update, is that I wanted to make sure, of course, we had plenty of exercise with the quizzes, but I just wanted to make sure. So if you have like a question like this with two blanks, right? When you look at the choices, these choices will be separated by a semicolon. This is a semicolon. Just make sure that you understand this. Do you have any questions about that? I think we did several of these on the quizzes, but just in case someone, isn't paying attention, I just wanted to direct your attention to that. Okay? These two, this is the answer, and it will be separated by a semicolon. Okay? And if it's only one, but you have two blanks, make sure that you pick a choice with two different, two phrases, words, whatever. All right. And remember to choose your best answer. There could be correct answers, but one of them is the best answer. So make sure you read all of the choices. When you encounter the first correct answer, don't just go ahead and pick it because it could be a correct answer, but it's not the best answer. So please, I can't stress that enough. Please read all of your options. Read all of the choices. When it's true or false, make sure that it's an and. It's an and, not an or. Both statements, or if it's more, all of the statements, not just one of them, are correct to be true. If even one out of, like I said, out of four, even three are correct or true, one is false, it's false. Yeah, we posted that sample. I will go over it with you because there are a few things that we want to talk about. This is not has not been changed, has not been changed. You asked if there will be calculations, and last time I said yes, but then when I met with the CBTF professor, who is my contact, he said you can't bring anything to the exam room, so you can't bring a calculator. But they are working on a toolbox that you can use. Maybe we will have it during the final, but for the midterm, that one question that I told you that involved some calculations will not be on the midterm. Okay. I hope that helps you relax a little bit. You already did a lot of calculations in your assignment, so I'm not worried about you knowing how to calculate the important parameters that you need to know how to calculate. I'm not worried about that. But unfortunately, we will not be able to include calculators in the or have you bring calculators to the exam. Same with, remember when I told you that I will include the nomogram that you can use to determine magnitudes, and you will need a ruler. You're also not allowed to bring a ruler. So remove that question as well. Maybe I moved it to the final exam. Maybe by that time we will have that toolbox and we can use it. Okay. These are your questions that you sent me. Are we expected to know how to read graphs, pictures, measurements, diagrams, etc.? You're expected to understand figures that we went over together, right? Um, or similar ones. But I'm not going to give you something that you is completely foreign to you and ask you to make interpretations. I don't think that's fair. Will there be questions that are from the readings? So I gave you two types of readings, right? I gave you readings and I gave you resources. A resource is something that, like when I remember how I do my slides, I always include the link, although it's people, you don't have to include a link on the slide, just cite your source. But I usually do that so that you can go and check the resource yourself or the source yourself and learn more about it. Because I have so much material to cover, I can't cover each source completely thoroughly. So that's a resource. And a resource is more of a, like an extra optional reading. As a student, I was always asking for more resources, so I just provide them in case you like them or in case there's something that piqued your interest and you want to investigate further. So I include those for you. But readings are something are materials that I expect you to prepare prior to the class. I will definitely ask you questions about the readings as far as we covered um, in the class. So they are definitely related to what we cover in the class. But if there are a few details in the, say, for example, it's an article, and there are a few details that we did not discuss in class, then I will not be asking you about them because some of them are very long and some of them include information that are not relevant to our class, to our course. There's another one. Yeah. Do we need to know exact dates? That's the one that's why um, I changed the study guide. So, yeah, a few earthquakes. You need to know the dates and roughly, the magnitudes. Just was it very high, but like 8 or 9 or in the sevens, so sixes, just roughly. But yeah, you don't need to memorize all the dates and details. But the thing is, I'm not going to ask you what year or what magnitude, but I'm going to refer to that earthquake. So, for example, I'm going to ask you about the Loma Prieta earthquake. I will also say of 1989, the San Francisco earthquake of 1906, for example. So, in that, in that context. Any questions before we leave that file? So I included the file, the updated file. I just needed my version just to, it's exactly the same as yours, but my version has the highlights. There's a question in the chat. Uh, and in what reference would it be? What do you mean? Um, there are some direct messages that, sorry, that I didn't get any notification for. Yeah, that's a good question. If you cannot find any availability with CBTF testing, like you can't find availability on the day that you're free, please talk to Evan, our GSI. He's one of our GSIs. Evan should be able to help you and let me know if you still need further help. Will the midterm exam include content from assignment 4? So it's up to lecture 14. Yes. If you give us a date and name, what would the question be about? It would be anything. It would be maybe was there fire damage? For example, I'm just making something up off the top of my head. Was there fire damage during the Loma Prieta 1989 earthquake? Or talking about what happened in the Marina District, because of the fact that, of the soil type, things like that. So I refer to the earthquake. I'm not gonna ask you to pick the year, for example. Okay. All right, I need to move forward. All right, so now you know where everything is kept, and I will put the video for this session as well in that module. Okay. Okay, I'm gonna share. Yeah. Oh, where did my video go? Oops, sorry. Okay. So I just wanted to point out a few things with CBT that they shared with me. So I'm just gonna test this, run this test with you. This is an orientation, second orientation quiz. Again, feel free to take their orientation quiz that they included for you if you want to. Like I said, there are like 1,000 sessions, and if needed, we can request more. But let's just take a look at what the things I wanted to point out for you. So this is what you will see, something similar like that. So let's just something similar to that. Let's just go to question one, and I want to make my first point, which is excuse me, which is the difference between invalid response and wrong response. So, say I get to this question and I just save, right, without answering. If you go back to the assessment overview, you will see that it's an invalid answer. So it means that you did not make a choice. So you can always go back and change, say, for example, change your answer. Okay, and then you can save and go back to the assessment overview and you will see that it was saved. You need to save because otherwise it will not record your answer. So you have to save. The second thing that I wanted to point out is that, okay, so the first thing is it will tell you if you don't have a, if you don't make a choice, and it will be called invalid answer. So remember that, okay, it will be called invalid. It doesn't mean that your choice is wrong. It just means that you did not enter a valid choice or a choice. And then if you can always go back and you can change your answer, right? And it will record, if you go back, say you go to another question, then you come back to that question, it will record the most recent choice. So remember that you can change your choice. And then let me go to the assessment overview. The other thing that I wanted to point out is what is the questions number that are prime? Okay. The other one that I wanted to point out is that you can report an error in the question. So this is not for kind of editorial, you know, comments, really. It's more of, you read the question and you don't understand it. And the reason why you have that is that we will not be proctoring in CBTF. So you will have CBTF staff, but if you want to talk to us, to the teaching team, we will not be available. What you can do is that you can submit a response. For example, there's a typo in the question that's preventing you. Of course, we will revise the questions, review the questions, make sure that they have no typos, no issues. The choices are unambiguous, of course. But say you want to report something that you don't understand or has like an issue with the question, um, you can just use that to do that. So to report the error or concern that you have. Once you click report the error, we will receive it on our ends. And during that week, we will be monitoring the reports. We will be making sure that we will try to resolve them as they come. So hopefully you don't need to do that, but in case you do that, then we will be able to see it. Now, say you read the problem multiple times, still don't understand, you still have an issue with anything in that specific problem, do your best on the question, try to solve to answer the question, report the question, and then after the exam, we will work with you to fix any issues. Again, we understand that we are not there to proctor, so I just don't want you to be worried at all. Okay. You can also use this attached file or notes if you want. Usually it's not going to be attached file, probably going to use this, add a text note if you want to use it as a scratch paper or something that you want to keep on the test. The last thing that I wanted to talk to you about is once you click finish assessment, you can't go back. That's it. The exam is done. You can't go back. So be very careful when you not to click that button until you are done. If time is up, it will be clicked for you and the exam will just finish on its own. Um, One of you asked me if there will be a timer. I need to ask the professor who's helping me or who's my contact with CBTF. I will ask him. So try not to click on finish the assessment until you're actually done. Like I said, once time is up, it will be automatically clicked for you. If you do that by mistake, please let us know. Don't worry. Don't worry. We will figure it out. We will help you, you know, get get your exam done still. Don't worry about it. I'm just letting you know that's not it's not the end of the world, but try not to so you can finish your exam and, not have any kind of stressful situation. But if that happens by mistake, please let us know. All right? And like I said, please go ahead and do the orientation quiz if you haven't already. And yes, you can do um, the orientation quiz that is available right now, in addition to the one that you did before. That's totally fine. They're different. I will go over what I think or what I have seen as the most important concepts or topics from experience. However, feel free to stop me and ask questions. If you are watching this, at home and, you're not with us today and you're just watching the recording, just email me. And if you email me questions about, sorry, did you want to say something? Let me unmute. Okay. Yeah, please keep your microphones on mute. So, if you have any question that's related to the material, I am happy to include that as well in the study guide if you send it to me on time. All right. So, oh, there's a question in the chat. Sorry. Oh, no, no problem. That's totally fine. So we don't need to discuss any of that. So um, I'm going to go over the slides, all right? And let me know if you need to stop, if you need me to stop. So we talked about, I introduced what the San Francisco Bay Area is because we talk about it a lot. It's where Berkeley is, which county. We talked about why learning about earthquakes matter. Uh, would you please do a PowerPoint? Yeah, sure. Yeah, yeah, sorry. I'll use the PowerPoint version. No problem. You're welcome. No problem. Sure, I can use the PowerPoint version. Okay. No problem at all. No problem at all. Okay, let me see. Yeah, I think I need to swap this place. Okay. Do you see the correct slides now? Can you just give me a thumbs up? Thank you. All right. All right. So that was the first lecture. We talked about, logistics. And then we talked about the San Francisco Bay Area, Berkeley, where it's located. And then we started talking about the cost of earthquakes. So what I think is an important topic, and I just want to quickly review it because sometimes it causes some confusion, is the difference between hazard and risk. Right. So, for example, here, a hazard is the presence of a shark in the water, but there is no exposure. There's no one that's exposed to that shark, right? And vulnerable to that shark. Because if our bodies are completely made of iron, even if we're exposed, but there's no vulnerability, right? Because we're made of iron, the shark will hopefully not be able to attack us. But if you have hazard, you have the presence of the shark, in our case would be a fault that is active and could cause an earthquake, and the presence of a person, so exposed to that hazard, then you would have what we call risk. Risk needs a likelihood of harm. You need to have a possibility or exposure to that harm. So there's another example I want to also go over. So one of you actually asked me about if this is a mathematical equation. It's not a mathematical equation. I will talk about catastrophe modeling in one of our lectures. I was a catastrophe modeler at I was a catastrophe modeler at some point, and it's really fun. I want to talk about that, and I want to talk about how the insurance industry uses these catastrophe models to calculate how much premium people pay, things like that, and what reinsurance is, things like that. So we'll talk about that definitely, and the role of catastrophes and seismic hazard modeling and risk modeling. However, um, for just for now, I just want you to know the difference between risk and hazard. So here, the hazard is the presence of very bright sunlight, and the vulnerability is the exposed skin, right? People have exposed skin, and it's 10 o'clock, so it's fine. And then by 1 p.m., after some time, you can see that there is significant loss or damage, let's say damage, not loss, but damage that occurred to these people because they don't have something to mitigate the hazard. And also we I gave you the slide that interprets that we thought was a mathematical equation. It's not a mathematical equation, it's just like a visual. Um, it shows you, oops, it shows you how risk is in the intersection of hazard, exposure, and vulnerability. So vulnerability is how susceptible we are. Like I said, if our bodies were made of iron, then our covered in iron, our vulnerability is not very high. And even if there is a shark in the water, we won't care, right? Even if the hazard is high, we won't care. Another example that I showed you also when we were talking about, I mentioned, was um, earthquakes in the middle of the ocean. It's a very high hazard, but the risk is not high. All right. Any questions about this part? Because it's kind of important that you know the difference. I talked a little bit about the cost of earthquakes, like the actual cost. I'm going to move forward through the slides just to get to the parts that I need to highlight. I gave you some numbers for that, some losses, just to show you the extent of the losses, just to show you how big of a problem it is. No, I do not expect you to memorize these numbers. Okay? I went through them just to show you the how big the problem is. There's a question in the chat. May I ask for the subduction zone in the middle of the ocean where a tsunami can occur and reach land? Yes, this is a risk. This is a risk. But if it's only the shaking and it won't reach land, then yeah, there is no risk. It can also reach land, but maybe there's no one there, right? You need a population. You need a likelihood of harm. You need someone to be exposed and vulnerable at the same time, not just exposed. People often forget vulnerability. If we're exposed, but we're good, right? We're fine. And the remember, I told you about the difference between the case of Japan and Haiti, right? Uh, Japan was struck by a magnitude 9 earthquake. Haiti was struck by a magnitude 7. We will discuss this as one of our very important case studies, and it's coming up in the coming lectures. The damage in the two countries was very different. Despite that Japan had a higher magnitude earthquake, the damage and the consequences were way less dire than for Haiti because the vulnerability in Haiti is a lot higher. There's a question in the chat. Thank you. You're very welcome. No problem. Can you share the question you're answering? We can't see the question. I'm not answering a question. Oh, you mean the question? It's in the chat. Sorry. I will read the question every time. So, sorry, I don't I can't share the chat because some people send me direct messages. They don't want to be identified. Um, may I ask for a subduction zone in the middle of the ocean? Oh yeah, you're sharing with everybody. Okay, thank you. I appreciate it. All right. And then we talked about this was a report that when it came out, I was at the USGS at the time when it came out, and it was very um, well received. So I was at a workshop at the time with the with attending a workshop with the USGS, and when it came out, and it was very well received. So this is a report by FEMA, and it kind of explains the expected, let's say, expected losses per year averaged over a long term. It's not what happens in a single year, right? It's just the um, average average expected losses over a very long time. What do you notice here? Oops, I don't know, my mouse keeps flipping. What do you notice here? California, right? Very high average annualized earthquake losses in California. And that's what we expected, right? Because of everything else that we studied later. We talked about also Bay Area hazard, um, especially specifically, and we looked at the annualized earthquake losses by county, right? We discussed that as well. Again, I don't expect you to learn numbers, just to know where the hazard is highest. So the Bay Area is in a place of honor, and so it's Southern California counties. And of course, we know why the rest of the West Coast has high shaking hazard, as well as tsunami for some places as well. I'm not gonna I'm not gonna talk about like depictions in pop culture. And then I showed you some uh, you know, some videos for various videos for earthquake shaking, and even footage from the San Francisco earthquake to prepare for the next lecture. All right, so I will go ahead. Any questions about the first lecture? Okay, let's go to lecture two. I hope we have time to go over everything. I will stay behind a little bit. You can leave whenever you want to. You don't have to watch the entire lecture. Now you can watch it later. All right. Okay, next, lecture two. Yeah, I have so many windows open. Okay, all right. So we talked about Bay Area hazards, and specifically the faults, the active faults in the Bay Area. And I did point out the connection at depth between the Hayward and Calaveras fault. I did ask my friends or my colleagues who model hazard on these faults, and they said that now it's a known connection, right? And it can cause larger than expected, than initially expected earthquakes on either the Hayward or the Calaveras fault because they're connected. And we talked about the different probabilities of having a magnitude of 6.7 or larger uh, on any of the Bay Area faults. In total, there is a 72% chance of at least one of them. And as you can see, the Hayward Fault has a higher probability than the San Andreas. Why? Does anybody remember? Because the Hayward fault hasn't had a strain or stress relieving fault in a very long time, since 1868, right? Great, thank you. We talked about the Loma Prieta earthquake. Again, stop me if you need to, but you don't need to memorize, just to roughly know when it happened and roughly the magnitude range. We talked about all the damage. I showed you footage of the damage, Oakland bridge collapse. We talked about the effect of rock and soil on shaking. I'm not going to show you the video because we don't have time, but you can definitely watch the lecture or watch the video separately. We talked about what happened in the Marina District because it's made on this man-made land. It's built on this man-made land. These homes and various buildings are on this unconsolidated type of soil. So when it's shaken by an earthquake, it's shaken a lot. So it's amplified. The shaking is amplified, and hence we have this problem of um, amplified shaking in the Marina District. And we talked very extensively about that, and I gave you several examples. This is Oakland and Chinatown, and we talked about the issue with masonry, especially, and how masonry does not really fare well during earthquakes. It's not very suitable for this for earthquake resilient construction. More from damage in Santa Cruz, etc. We talked about that. And I also talked to you about why the city of San Francisco has this flag of a phoenix rising from the ashes. We talked about it. We had um, uh, good discussion about it. And um, when we were in person, I was really surprised that a lot of my students had seen the flag before, but they never thought about what the bird um, what the bird is. All right. So previous earthquakes, they did have previous fires in the San Francisco Bay Area. And the reason why I was showing you these earthquakes or discussing with you these earthquakes is that, let me go ahead and show you the rest of the slide. The reason why I talked to you about that, these previous earthquakes, not just to establish, a historical context of the various seismic events in this area, in the Bay Area, and especially in San Francisco, near San Francisco, but also to tell you how there was this building of knowledge and culture towards the 1906 earthquake. There were prior earthquakes, and it caused people to start to think about their vulnerability to earthquakes. And talked about what how the fire department became one of the best in the world because of that. So in 1836, there was one on the Hayward Fault, epicenter near Oakland. 1838, San Andreas Fault, epicenter near San Mateo. 1865, again, near the San Andreas Fault. This is the one on the Hayward Fault that we will talk about again, the 1868 epicenter near Hayward, about a 6.9. And just for context, the university was founded in March of 1868. There were during the gold rush, there were about six fires, right? About six great fires that destroyed large parts of the city. So again, these are one of the reasons why the San Francisco Fire Department became one of the best in the world, like we discussed before. We don't need to talk about that. I will be skipping slides because there's just so many of them. Let me know if you want me to stop. We talked about the issue with how to determine how they did scientists went back and tried to determine the magnitude of the earthquake, the San Francisco earthquake, and they ended up picking, a range. It was okay, it was between maybe 7.7 to 7.9. On the website of the USGS, the event page, like I taught you, it's 7.9, I think. We talked about fire damage. Again, stop me if you have a question. Um, this is City Hall and the Ferry Building view after the fire. This is present day. We discussed the article. I'm probably gonna skip slides regard um, that. Yeah, I did. Okay. Yeah, we discussed the article a little bit as well. This article that I assigned. Earthquake preparedness. Do you have any questions on earthquake preparedness? I think you had enough review of earthquake preparedness, given that you just finished a multi-part project about preparedness. But is there anything that you wanted to ask about regarding preparedness? I think you did your own plan. You made your own plan. You made your own. You prepared your own kits. You checked your homes and buildings for hazards, and you wrote a report about that. You had a quiz about it as well. Is there anything else that you wanted to ask? Because I'm not going to go over that part. It's something that we reviewed very thoroughly before. Any questions? Okay, great. All right. So we are done with let me check. Is there anything else? No. We are done with lecture 2. Let me go to lecture 3. All right. Yeah, it looks like we will go over time a little bit. Feel free to leave if you need to. You can watch later. Okay. Make sure that you're seeing the correct screen. All right. Okay. So we talked about, the various different setups for drop cover and hold on, people with walkers, chairs, canes, etc. Um, I shared some resources with you. We talked about how to assess your building that you live in. We talked about, how before modern science, there were many cultures that explained earthquakes through stories of, giant creatures, various creatures, catfish, frog, snake, turtle, sled dogs. So these were myths that reflected early attempts, let's say, to explain natural disasters through what people could observe and imagine at the time. And then Aristotle believed that the strong winds inside the earth caused earthquakes. We also discussed that. We talked about how in Christian Europe, earthquakes were often seen as acts of God or punishment for um, sins or warnings of, helping people to repent. Um, we also talked about then how during the 1600s, 1700s, there were natural explanations began to replace supernatural ones. And the European thinkers, started to uh, connect the dots and, think, okay, we think that there might be a connection between natural or physical phenomenon and earthquakes. We talked about the Lawson Report, how it really changed our understanding of how and why earthquakes occurred. We talked very extensively about the Lawson report, how they catalog description of earthquake effects, identified the San Andreas Fault, uh, we talked about all the maps. I went over the maps one by one of the fault location and ground shaking distribution and how that has eventually led to or helped the development of the elastic rebound theory, which explains how stress builds up along faults and then suddenly released during earthquakes. I'm just going to go through the slides. Talked about how, um, there's another one, how the shaking near the fault was highest, but also then you would go through an area where shaking was a bit less, and then the shaking would amplify again because you are close to soft bay mud. I had you virtually do that exercise. I asked you to look at the picture and pick one of the MMI intensities. Usually, when we were doing that, like sometimes in the summer, we do that. We do whole live lectures, and I had like a poll, and students almost always got the number that I had on the screen. Almost always. We talked about Did You Feel It surveys and how they the citizen science helps fill in the gaps and can be very valuable data. This is a comparison between instrumental versus did you feel it shaking. We talked about earthquake sources, where earthquakes occur, the death toll. Again, if you're asking whether you need to memorize these numbers, you do not, but you need to, I needed to explain or to show you how serious earthquake, how serious of a hazard earthquakes are. Fatalities in the 21st century, very, very high toll. We talked about what's in the interior of the earth. Again, feel free to stop me, or if you are watching the recording, feel free to email me questions. We said faults are the source of earthquakes, right? We explained the difference between a hypocenter or focus and an epicenter. So the hypocenter is where the earthquake occurs, is where the earthquake starts. Okay, it's the starting point. So it's not in the middle. It's not, it can be, but it's not in the middle. It's not like on the left, right. It's where it started, regardless where that is. And the epicenter is directly above that on the surface. There is a question in the chat. For me, selecting the right number for MMI is hard since I sometimes visually assess the damage incorrectly. Yeah, there will not be a question like that on the exam. No, it's very subjective. It was just an exercise. No, it's very subjective. It's too subjective to be fair. We talked about earthquake sources. I went over each of these images or figures or photos myself and explained it to you. We said a fracture in the raw, a fault is a fracture that has had movement. Some people say fractures are, oh, if a fault is small, they say it's a fracture. No, a fault is a fracture. It's a crack in the earth that has moved. If it has moved, regardless of size, it can be tiny. Remember man-made earthquakes? It can be very tiny, but they're still faults. Yeah, people sometimes refer to them as fractures, but that's not correct. A fault is if the crack moved, right? If it has some slip, that's a fault. We talked about the Elquist parallel earthquake fault zoning act that was passed in response to the 1971 San Fernando earthquake to make sure that people don't build structures very close to fault zones. I also virtually uh, did this exercise with you. I asked you to think about this. Um, So by California law, active fault means the fault has moved within the last 11,000 years. And when we were in person, almost nobody guessed 11,000. So if you didn't the first time, it's yeah, that it's very common that people don't guess that. And it sets back for new construction, they need to be at least 50 feet from a fault trace. We know that the Berkeley Stadium is right on the Hayward Fault, and we said that because it was built before, it's already there. It's not a new construction, so they just did retrofitting, and we will talk very thoroughly about the retrofitting of these Memorial Stadium. Sorry. Whether the faults are still active. We talked about the evidence of active faults. There's a question in the chat. Is it safe that the Memorial Stadium? Yeah, yeah, they built it in such a way that even if the fault moves or there's slip, it will not cause any structural issues and collapse. It's yeah, it's safe. We'll talk about that. Yeah, I this is a question that I get almost every year about it. You know, is it safe? We know it's and even before I bring it up, sometimes students bring it up themselves. So yeah, we talked about evidence of active faults, evolution of our understanding, how, you know, they started with Snyder and Taylor. Um, some of the evidence, right? First, the fact that the continents fit like a puzzle, pieces of a puzzle. A question in the chat. What would happen if an earthquake happens during the football game? It's not going to collapse. Yeah, if this is what you're, it's not. It's designed in such a way that it does not collapse. You will definitely feel the shaking. There's no way around that. And you need to cover, you need to make sure that, you're safe yourself, you can protect yourself. But yeah, it's not going to would it feel stronger? We will talk about that as well. So there is shaking, right? That yeah, I'll talk about that. So we'll talk about the ha factors that affect shaking, but you're very close to the fault. So yeah, the continents fitting like pieces of a puzzle, right? That's another one. We also talked about, yeah, this is the how the continents fit together. We talked about, how they started as one and then ex broke up and expanded away from each other. Um, they started as one and then they moved out and away from each other. We talked about how they found fossils of animals or plants that couldn't have crossed oceans, right? And they found um, records of these, or they found these fossils on various continents that are today separated by vast bodies of water, and that can only mean that the continents were connected at some point. We also talked about this apparent pole wander, and this particular slide is relevant to the pole wander, and it's relevant to the stripes on either side of a mid-ocean ridge. I explained the physics, I think, very extensively. But let me ask you, do you want me to go over this again? Or was it okay the first time? Okay. Yeah, I usually get this question. Okay. Electricity and magnetism are, manifestation really of the same phenomenon. It's called it's just electromagnetism, right? And magnetism is really caused by motion of charge, and in some elements or materials, they have a what we call a magnetic dipole, like the electron is moving, so that's charged, it's moving, and it causes magnetism, right? It causes what we call a magnetic dipole. If the electron is matched with something that is an opposite, right? It's, causing the opposite dipole, it's then there's no magnetization. But in many of these rocks or minerals, there is an unmatched or a remaining or an effective net dipole. So when when the when the lava starts to come out, it's very hot. And because it's very hot, those little tiny magnets in the rock, the rock is very hot and the magnets are free to move because the atoms are free to move, right? It's liquid. So they're free to move. It's not like a gas, they're free to move everywhere, but they can move around. So what happens is they align themselves because they're magnets. So and because they are immersed in the magnetic field of the Earth itself, they align themselves with the magnetic field of the Earth. And then they start to cool down. When they cool down, they can't move anymore because they became solid, and it preserves this direction of the magnetic field of the Earth at the time of their cooling down. Okay, that's a question in the chat. Okay. So yeah, that's it basically. Do you have a record of the where the orientation of the magnetic field of the Earth at the time when these rocks cooled down? Apparent pole wander, we talked about that. It's the same thing. These rocks preserved the location of the when the continents were closer together. They were all pointing towards the magnetic pole. And then after the continents broke apart. The continent broke apart and they started to move away from each other. They started pointing at different locations today, right? But that does that mean that the pole was moving, or that doesn't make sense, right? It doesn't make sense that the pole is at different locations at the same time. So the explanation that made sense is that it was not the pole that moved, it's the continents that moved apart. We talked about bathymetry, mapping the bottom of the ocean. We talked about, mid-ocean ridges, where the shallow earthquakes are, where the deep earthquakes are near the trenches, how they are deep. So this is again the same concept of, preserving the magnetic field of the earth. So when these are how we related this information to the knowledge that new crust is formed at these spreading centers is that we found that we see on either side of the mid-ocean ridge, we see on either side these magnetic stripes that also indicate the reversal. There's a periodic reversal of the magnetic field of the Earth, and you can see that happening on either side, and it's symmetric. So this means that as the rock comes out as the lava comes out of the mid-ocean ridge and it starts to, spread, um, it starts to cool down and preserve the magnetic field of the Earth at the time. As it reverses, the magnetic field that it points to will also reverse. We talked about global seismicity and how it's not random, right? It's seems like it follows a pattern, and we also talked about these very deep earthquakes that happen near the trenches, right? We saw how the bathymetry and seismicity patterns match, and they outline the tectonic plates. Here, these are the shallow earthquakes. They shallow seismicity, they also outline the mid-ocean ridges and the deeper ones or the deep ones, they outline the trenches. Any questions? All right. I think this next one, and maybe a couple more lectures that we really need to kind of stop and discuss a bit in a bit more detail. But otherwise, I think it's we can just go qu quickly over. Yeah, I don't know what you're seeing. Okay. All right. So we talked also about the Kobe earthquake, right? 1995, and how, sorry, and how it's similar to what we can see here, in the Bay Area in an urban area, um, with a lot of large population as well. It's a finite fault, right? It's not a point source. It's a finite fault. It has, it's a plane. We talked about that. Was close to the city of Kobe, unfortunately, and caused a lot of damage. We talk about the lessons learned. These are all summarized in the study guide, so you can just go ahead and take a look at the study guide. We talked about, this is freeway failure. We showed the difference between old and new liquefaction. So liquefaction, especially, so if your building is on we've talked about we define the word non-consolidated sediments or non-consolidated soil. We said that these are more loose and will amplify the shaking, right? If an earthquake occurred. And also you can, if you're very close to the bay or you're very close to water in general, you can also have that effect, right? Because the soil is saturated with water. You can have lateral spreading or subsidence or, general evidence of liquefaction. Talked about fires. We know fire after earthquake is a significant hazard, cascading failure. So one issue causes the other. Like, for example, if the water pipelines start to break, then it will be very hard to put out the fires, things like that. We also discussed that. Evolution of our understanding. Um, we, talked about how there is a now we agree that there are about 12 major plates that the 12 major lithospheric plates that move in different ways with respect to each other. We talked about what drives the plate. I explained to you the three different main ways that heat is transferred: convection, conduction, and radiation. We are mainly concerned with convection, and where conduction that leads to convection. Convections are the currents, and I told you why they happen because of these density differences. And if you look at a water boiler or kettle, and it's like the see-through kind, you can see these currents happening because of the water heating up, expanding, and then floating to the surface and being replaced, etc. We covered that in great detail. Um, this is what drives the plate. So it's this convection currents set the stage, but really the slab pull and this diving, this with gravity, this diving of the subducting slab underneath the overriding slab, it really, really helps drive this motion, and it causes this ridge push as well. And it helps drive the plate motion. We talked about how an earthquake happens, elastic rebound theory, how because of tectonic loading, the faults start to build strain, which is this deformation. We talked about stress, what stress is. It's the force per unit area. I explained to you what it means in a rock. And strain is the response of the material, in this case, the rock, which with deformation to the stress. And then suddenly this energy, this deformation is relieved and the energy is released. And we talked about the earthquake cycle, how, as crustal strain rises and then an earthquake occurs and then suddenly falls. And we discussed these in detail. We talked about the various plate boundaries. This is an important figure, right? It tells you which plate. Again, I don't expect you to know the names of the plates, all of the plates, but some of them we discussed in detail. And like this is a subduction zone because it's colliding or subducting. Um, this is clearly divergent. This is transform. So we talked about those as well. Transform is this side-by-side motion, subduction or convergence. It can be one going under the other, or it can be collision, like in the Himalayas, for example. It's responsible for mountain building. This is divergent. We talked about black smokers, and I talked to you about how they are a rich environment for, various ecosystems in the ocean. Talked about divergent um, boundaries as well, like in the Red Sea. I explained to you what bathymetry is just to make sure because the lecture before I did not go over the details of bathymetry. So this slide is useful if you didn't get it for in the previous lecture, because I realized I didn't explain what bathymetry was. And then here you have a mid-ocean ridge that's offset by what we call a fraction zone, a transform fault. So call that a fracture zone. We talked about the San Andreas. It's a transform boundary, convergent boundaries. There are three main types, right? There is ocean-ocean, ocean-continent, and continent-continent. And we talked about how continent-continent, like the Himalayas, causes the mountain building. I gave you one example of each. Then we talked about faulting regimes. So because we have these three kinds of boundaries, we end up with three kinds of faulting. Um, Normal, reverse, strike, slip, right? I showed you these videos of each. This would be normal, right? The hanging wall falls. The uh, the thrust fault or reverse fault, it overrides strike, slip, side by side, okay? We talked about the different terminology, what a dip is, right? And a strike. We explained what a hanging wall, what a footwall means, and even why they were named as such. This is an example of a normal fault, right? We talked about they happen in extensional environment. Reverse fault, they happen in compressive environments, right? We have one overriding the other. We talked about strike slip faults like the San Andreas, like in Wallace Creek. We talked about the difference between left lateral and right lateral faults, right? So the thing is, no matter where you stand, you will see the fault moving in the same sense. So if you stand here, you will see this is a right lateral fault, like the San Andreas and the Hayward, for example. If you stand here, you will see it moving to your right. If you stand here, you also see it moving to your right. This is an oblique fault, so it has two motions. It has a dip slip and a strike slip combination. Yeah, here's me explaining stress. I also walked you through the Anderson classification. I got a question, but not from you. I got a question, I think it was maybe last year about that. Um, you Yes, you need to know, and it's in the study guide. And I think it's really nice in the study guide because I always keep SV in the middle and you can see how SV changes location. So we talked about the three principal stresses, right? We talked about why in each case we have here, for example, if SV or the weight of the overburden is the highest, how it takes the block down, it moves this moving block down because there's really nothing to keep it there because not much, let's say, to keep it there. Um, so it moves down. You need to know these relations. So what it will be for a normal, what it will be for a strike slip. For strike slip, the largest or principal horizontal stress or SH max is the highest in this case. Um, and it's also the study guide, like I said. So it's the highest in this case. However, SV is still not very low. It's right after SH max. If it's the lowest, then um, you don't have much weight from the overburden to keep the wall from overriding. So that's why it just does it. You get squeezing from the horizontal stresses, so it just overrides. And SV is not large enough to keep it from doing that. We talk about special cases. Oops. And you solved that, I think, in your, was it assignment two? You did solve these problems, and you did very well. There will be two, in this case, there will be two possible simultaneous possible regimes. So you have what? Strike slip normal in this case, and here you have strike slip reverse. We talked about that very thoroughly. Here's the case of a caldera collapse. So the magma chamber gets emptied out, and then you get the caldera collapse because SV is so much larger than the horizontal forces. I think we will do another half hour. Okay. We talked about whether a fault is still active. We talked about how in this for example in this example where you have uh there is a pull apart, right, in the um, along the fault, and you get this because it's like you're pulling on a rubber band, right? So you get this sagging, and it fills up with water, and you get a sag pond. Or if it's like pushing, because this side is pushing, this side is pushing, and the result would be that you have this compression, so it becomes a push-up bridge, and you see these um, along uh, along the strike slip faults in many cases. Question in the chat. If we're unable to stay, will all 14 of the lectures be covered? Yes. Yes, I'll do another half hour. If not, I will end the lecture and I'll just record it on my own. But I'm just I really wanted to go over the physics parts because that's where I got like questions. I used to not dwell on them too much, but the students actually wanted to and enjoyed talking about like heat transfer and magnetic dipoles and things like that. So I'm happy. I'm always happy to talk about physics. Always happy. And I that's why I tell you, I want to minimize stress in the course because I want you to enjoy it. I want you to love it. It's the most, for me, it's the most enjoyable thing ever to learn about nature and how things work. And you're my students. I want you to be happy. I want you to enjoy it as well. Um, there's a question on that. Thank you. Oh, you're welcome. You're very welcome. I'm happy that you're enjoying this. Okay. Channel offset at regular intervals at times. So total offset here, for example, here for from the modern channel. Remember, because we said that the fault will keep offsetting the channel, and then eventually the channel will not have any water going through it, and the creek will etch a new channel. So, and just, flow through it. So the offset was about 130, and we did carbon dating and figure out that was like 3,800 years ago, 3,800 years ago. The slip rate would be in this case 130 over. So remember, speed is distance over time, right? So distance over time. And that's on average, right? Remember, that's an average, but it doesn't mean that it slips by that much every year. If it's a locked fault, it will do that slip with the earthquake, right? On average, but yeah, depending on the earthquake. We talked about the Hayward Fault. I'm going to move through it. So at this location, we calculated the offset, if you remember, to be about 10 millimeters per year. Overall, it's about 9. And it's significant slip. We talked about the hazard on the Hayward Fault because there has not been a large earthquake since 1868, and we talked about how there are evidence of creep. There were no major earthquakes, and you see these um, uh, displaced curbs and various evidence of fault creep on the surface, despite that there were no earthquakes, and we know that's because of fault creep. So it's been, how did we calculate that um, creep? I'll show you. So this GPS stations. This is an example of steady creep. So it just keeps happening, right? And this is where the fault is locked, and you see this deformation until it ruptures and is released. We talked about evidence like this is in the old stadium. Um, Again, evidence in the fence here as well, right? Uh, Creep, evidence of creep again. And we said that there will be hybrid behavior in the faults. There will be aseismic creep and seismic earthquake stick slip that we talked about to like the hair, and the creep is more like the tortoise moving slowly. Yeah, so both creeping and locked also is possible, like we said, and I explained that figure in detail. This is creeping, and there's also the locked asperities and also the creeping parts as well, and they can happen on the same fault. And sometimes there are depths that are creeping, and then the rest of the fault is locked. So yes, creep does relieve some of the strain, and then the rest will be relieved with an earthquake. So this is the total slip per year. Some of it is relieved by strain, creep. The rest will be relieved by uh, that's amount left for an earthquake relieved by an earthquake. We talked about how we place these benchmarks and then the benchmarks to follow how much to follow the creep or measure, quantify the creep, to measure and quantify the creep. So we use these GPS sensors, and I explained to you how they work. We take multiple measurements and we calculate how the motion progresses with time. Okay, I will go now to the next lecture. I don't think yeah, I think we can move a bit quicker. Let me just stop me if you have any questions. But I used to have a new slide deck with only the slides that I think are relevant, and um okay, and students asked me to not do that. So they asked me to show all of the slides because they'd be, oh, but Professor, there is a slide that I would like to show you. And then I would have to go back and pull up the slides. So that's why I'm just going over the lectures. We talked about our modern understanding um, of tectonic plate tectonics, talked about the Ring of Fire and how so many of the large earthquakes and earthquakes in general, most earthquakes occur around the Ring of Fire on the Pacific. We talked about how the Marianas Trench is the deepest point in the ocean. That's the Challenger Deep. We talked about that because students always made the connection to the movie. Um, we talked about the again about the types of plate boundaries, how we understand them in modern times. I don't need to repeat that. I talked to you again about more in more detail about how we measure plate motion using GPS stations, and we just attach these um, receivers to anchor them to the tectonic plate, and then we just follow their motion, and we get the average slip rate from that. Oh, you need to go. And then we started talking about seismology. Seismology is the study of earthquakes. Uh, and I wanted to do just a couple of things here. One of them is the physics part. But remember, there's a difference between seismometer, seismograph, and seismogram. Seismometer is the sensing motion, like it's the sensor that senses the motion of the ground. And it's part of the seismograph, which is the instrument that has everything. And then the seismogram is the record itself. And we talked about like the early seismoscope. This is the one I wanted to go over. Do you need me to go over that? It's just the principle of operation of a seismometer. It's basically it's an inertial sensor, so it's a mass that, Einstein, Newton's laws, the first law, inertia, right? Objects resist change in their motion. So if you have like a pendulum or a mass that's suspended, the rest of, if you suspend it, the rest of the instrument will move and the mass will not move as much. So that's why it will give you a relative motion and it can record that relative motion. So that's the principle of operation of really all modern sensors of motion. We talked about of ground motion. We talked about the early seismometers. It was fun. I explained it in detail. You can go back to the lecture if you want to. We talked about the Wood-Anderson seismograph, which eventually will become relevant. We talked about modern seismometers and how they're three component, etc. We talked about the waves. We talked about how they travel through the body of the Earth, the body waves. S&P, they travel through the body of the Earth and they change paths because of the changes in physical properties. We talked about how waves are longitudinal, so you and the particle motion, the we talked about how the medium moves, right? And then it only vibrates or it oscillates about its equilibrium position, but it doesn't actually move. Like there's no displacement, there's no net displacement. It just vibrates or oscillates about its equilibrium position and it just goes back to how it was. But the wave itself, the energy propagates. Let me just quickly show you what I mean. And in this case, particle motion is in the same, this is the way where the energy is moving this way, and so is the particle. They're both perpendicular in the same direction. In an S wave, it's like I showed you how that works. It's the motion, the oscillation of the medium is perpendicular to the wave motion. So the wave itself is moving this way, but the medium is oscillating. So if you look, so it's like my hand is going to go up and down, but so it's in this direction, but the wave itself is moving in this direction like this, right? That's not very ideal, but I did show you a few videos on that. You can go back and check. You have any questions about that? All right. And we talked about shadow zones. The P wave has a smaller shadow zone than the S wave because P waves are compressional or longitudinal waves. They can travel through any medium, while S waves cannot travel through liquids. So once they hit the outer core, they stop. Whereas here, it's just because of refraction that that we have this shadow. It's not because the P waves can't travel through the medium. They can. Same here, just reiterated. Then we talked about surface waves. They can be very damaging. Talked about love waves. And Rayleigh waves, they have this rolling motion that can be also very, very damaging. I made you this table that kind of summarizes the differences. We talked about source studies, how we need and why. I explained these equations in great detail, how we utilize the difference in arrival time between the S and P waves because they have different velocities and it can be very helpful and how we need at least three stations. Now we have so many, but at least three stations to determine the location of the earthquake, because with the first one it gives you just a radius around a point. With the second one you have to, let me move these controls. Oh, I can point here. You have 2 points. Okay, so the earthquake can be here or here, but then so you need a third one to give you the last data point that you need and to get this intersection of all three. I kept going, explaining more. This is to show you how the first arrivals from explosions are always positive, and I explained that this is by convention. Up is this positive is compression. I explained to you focal mechanisms are beach balls. I explained to you here this is a push, so this quadrant will be compression, and this one will be a pull, so it will be a pull, so it's more of an extension. Explained. This is a mark of a strike slip fault. For normal faults, the heart of it, I told you how to remember, but we did go over uh, why why they look the way they look, so feel free to watch the lecture for that. But just the key thing I want you to remember is that the core of a normal fault is extension, so that's why it's the white core, because that's what we designate extension with. And then because thrust faults are reverse thrust compressive, the heart of it, the core of it, is compression, so it's black, or yeah, that's what we uh, chose to designate it. They also indicate strike and dip, and we talked about that. I'm telling you that these are important. Please do review that lecture if you want to. I already told you what you need to know, but if you want to know more detail, please do review the lecture. But yeah, these are mid-ocean ridges, so they are extensional, so that's why it's this kind of beach ball for normal faults. And this is a subduction zone, so it's compressive and it's still like it's dipping. So you can see this the strike also is represented. These are important, okay? These are important. You need to understand what each beach ball means. Same. We need to, yeah, so we are done with this lecture as well. Yeah, I used to have a deck of slides for the review, and then my students requested that I go over everything really. Okay, I'm probably gonna end in 15 minutes, and then I'm going to end the session in 15 minutes, and then I'm going to just go ahead and review the rest. Did you have any particular lectures that you would like for me to go over? Any concepts, anything that you have a question about since we're here? All right. Could you possibly share the deck of slides you consider most important as well? I didn't make one. Like I said, I used to do that. I used to do that before, but then my students would want to refer to slides that I didn't have because I didn't think were important, but they wanted to. They wanted me to go over. So I don't have, uh, yeah, I don't have one. I would just make sure that you have at some point reviewed the lectures and go over the study guide. So we talked about source studies. They help us with locations, moment tensors, discrimination. So we next is discrimination. The difference between the seismograms of a an earthquake and a bomb, right? There's very different. They're very different. Bomb is shorter. You don't see a clear PNS wave. Um, it's the if you compare, right, whether it's a bomb or like an explosion, let's say not just a bomb, can also be a nuclear test explosion. You can also use focal mechanisms using seismograms. You can tell that this is the, again, no clear PRS wave, and you can tell that this is the earthquake and this is the explosion. Uh, this would be it's all compressional for there's no extensional parts, so it's all compressional for the explosion. Whereas in any kind of faulting, you have both black and white, right? And yeah, multiple ways. This is another one. This is a another example from North Korea. This was an earthquake, and this was a bomb test. And you can see primarily P waves, and then the S and surface waves are not primarily really compressional. Yeah, these are the focal mechanisms, earthquake versus bomb. Again, also the length of the uh, they're comparable, the length of the rupture. We talked about how rupture spreads, how ruptures develop. How I wanted just to make sure that you understand what the concept of the hypocenter, where it starts. Uh, we talked about rupture studies, how humans tried, with the Cola Deep uh, borehole to dig very deep into the earth, but they reached about 12 kilometers and then they couldn't anymore. We talked about the various methods. We are, so just FYI, I'm not going to ask you about the geophysical methods yet. When we go over the sensors and devices and instrument lecture, we will talk about these more. So this is more for the final, but I was kind of just giving you a quick introduction to that, but this is more reserved for the final. But definitely feel free to learn more about that. So an indirect probe into the earth would be, we can't dig a hole deep enough all the way, right? We stopped at about 12 kilometers because I told you became very, very hot and the rocks were really very difficult to drill into. So we use the indirect probes, which are earthquakes, and hence we can use seismology. We can tell from the difference in how far the S wave traveled, how far the P wave traveled, that the um, outer core is liquid because the S wave couldn't travel. Um, yeah, we learned a lot about that. So why is the inner core solid? Right? It's because of the pressure. Despite that it's not a low temperature or anything. It's very high pressure. What are the frontiers of seismology? So we have the earthquake. The source studies. The next one is what can seismic waves tell us about the Earth's interior? So we have the earthquake. It interacts with the Earth structure, and it comes out we can record that in our seismograms. We talked about tomography, how we start out with some model of velocity, and then we adjust that based on what the travel times that we observe, right? from the Earth. And then say, for example, here, if it's slower, then so I start out with some velocity, but I actually see that the wave is actually slower than I thought because of the travel time is higher than I thought. Then um, I can adjust my model accordingly, and I can do that in many directions. This would be a faster than I thought, and then I would start to make these maps of seismic velocity, and it really shows you inside the Earth. You can tell so much by looking at velocity. You can tell about the chemistry, the chemical composition and mineralogy effects on seismic with the effect with these effects on seismic velocity, you can tell something about the chemical composition and about temperature. Okay, and you can make these. We talked very extensively about these as well. I also talked to you a little bit about the global seismic network because it's very important. GSN is very important. It's around 150 stations around the world. And I also talked to you about another one, which is the IMS from the CTBTO, the Comprehensive Test Ban Treaty Organization. They all monitor earthquakes for various reasons and they serve each other. There are other seismic networks as well. And I talked to you about earthquake catalogs. I even taught you how to go ahead and um, find a particular earthquake that you want to find on say, I think I showed you, the demo was through the USGS catalog, or you can search the USGS catalog for a all the earthquakes that meet a certain criteria or are in a certain region. I showed you how to download also a spreadsheet of all of these earthquakes and what will be on that spreadsheet. And I gave you other examples of different earthquake catalogs. All right. Okay. I'm going to stop here and I'm going to record the rest of the lecture for you. Let me know if you have any questions. I'm going to send you the rest of the lecture sometime today. But yeah, let me know if you have any questions. Do you have uh any questions? Any particular lectures, any particular slides that you want me to focus on? Thank you. I was wondering if there was a previous review session last week on the 5th. No, that was a Q&A session. I just wanted to connect with you and see if you have any general questions on the course and discuss the midterm because we are using a new system. We're using CBTF. So no, there were no material reviewed, but please go ahead and review it. It's just 45 minutes. Just to understand how the midterm will work. Okay, thanks so much. Is it posted? Yes, it's in that module. It's in the module that I showed you, the midterm module. You're very welcome, no problem. All right, have a great day and good luck. Let me know if you have any questions. Remind me if I forget. Oh, you're very welcome. You're very welcome, no problem at all. Thank you. Take care. You're very welcome. Goodbye. In lecture 7, we talked more about earthquake intensity again, what it means, how it describes, how shaking is felt at a specific location. So it's a particular location. It's not a unique number like a magnitude, for instance. That's why we needed magnitudes, right? We talked about consequences of shaking, how intensity is determined. This is the MMI scale, right? It goes for also beyond 10, but that's not, I think I have, yeah. So we talked about its history, right? It goes beyond we beyond 10 we have 11 and 12, or we call them 10 plus to describe extreme destruction, but that's in not in all of the maps that you will see. We talked about shake map, right? And how Shake Map is extremely helpful to people who are, modelers, to people who want a rapid damage estimation, emergency response planners, where to identify, how to identify the hardest hit areas, etc. Um, and later, after the earthquake, because it's very quickly published after an earthquake within minutes. Later, how to improve building codes and hazard maps. We talked about, I showed you, I talked to you about some examples of that. I showed you this example from how it's on the event page, right? This is my earthquake of choice for demonstration. Um, yeah, I talked about this cumulative shaking map of for California. Um, Anything that I need to stop at? Okay, we talked about how we reconstructed um, Jack Boatwright and Bunduck. They reconstructed the shake map for the 1906 earthquake. I shared with you about this paper, some of the work they presented as well, in the various parts of the Bay Area. We talked about PGV, which is the peak ground velocity, why it matters. It's very strongly correlated with structural damage, matches how building respond dynamically. It's better predictor of building damage than displacement alone. And it's widely used. It's like I said, it's widely used, especially with hazard modeling or seismic risk modeling. We talked about PGA, which is peak ground acceleration. It measures how quickly the ground speeds up and slows down. It represents the forces on the building, right? Because it's acceleration, right? F equals ma, right? Like we said, we always come back to Newton's laws. Controls how objects start moving or fall over. Important for short, stiff buildings, structures, and we talked about why. What affects shaking versus local member shaking is not like magnitude. It's not a unique number. It's especially for that particular location. Local geology. We talked about how, because of local geology, even if you have earthquakes that are comparable in size on the west coast, they would be felt less widely. On the East Coast, they would be felt more widely because the crust is colder and older, and and causes the shaking to spread a lot more widely than this newer crust on the West Coast. The depth of the earthquake, I showed you two comparable earthquakes of different depths, and because of that, if you look, the shake maps are very, very different. Um, Magnitude, the size of the earthquake really matters. These are two earthquakes at the same location, but because the magnitude here is very high, it's much higher, it's 7.8, here's 6.9. So um, you can see that there's much widespread shaking than the smaller magnitude. We talked about directivity, right? And how where you are with relative to the rupture, so the configuration of the U rupture system, or not U specifically, but where you are determining shaking or where you're estimating shaking. Where you are matters. I explained to you, how this is kind of a neutral location, but if the rupture is moving away from you, you feel it less and with a smaller amplitude. If it's coming towards you, it's more the frequency is higher, so you feel the maximum shaking more, and as well as larger amplitude. I gave you another example for directivity. We talked about how magnitude is this single number for an earthquake. That's a unique number, regardless of where you are, regardless of who is measuring it. We talked about the development of the Richter magnitude, what it means. We talked about how it relates to the Wood-Anderson, the amplitude on the thermometer, the Wood-Anderson seismometer. And I explained the nomogram. Like I said, unfortunately, you won't be able to determine the magnitudes on a nomogram, but I can still give you a nomogram without like asking you to, like, if I can join, I can give you a different question with a nomogram still. So the nomogram basically gives you the magnitude based on their amplitude reading from the seismometer and the P minus S minus P time. Okay. We did several examples. Can go back to that. We will not have you did very extensive calculations in your assignment too, so we're not going to do more calculations. This is the Currently that's the similar to the Richter scale. Richter scale is not used anymore. Now sometimes we refer to local magnitudes. Body wave magnitude is important for discrimination, and so is the surface wave magnitude, as you can see, because explosions do not excite surface waves as very well. So the MB is usually larger for explosions than for earthquakes. We can use it in discrimination. We talked about what the seismic moment means. It's really related to the size of the part of the rupture, the fault that rupture size. Then we take the seismic moment that also is related to the energy released, and we calculate the moment magnitude. Um, Seismic energy as well. We discussed how it's calculated. We talked about the magnitude frequency relation, Gutenberg-Richter relation. Um, it relates the number of events to their magnitude. And as you can see, um, there is a 10 times as you go up in magnitude, the number of earthquakes occurring goes down by 10. For energy, as you go up one magnitude, it's about 32 times the energy. So if you go two, it's 32 times 32 is almost 1,000 times the energy. I told you how much I like this figure. This is the new one from Earthscope, and it really shows you how many, if you compare small earthquakes to the larger earthquakes in terms of magnitude, the much smaller magnitude earthquakes will be so many compared to as you go up on the magnitude scale, they become less and less, and similarly with energy. And we talked about, we talked about the different earthquakes that we are familiar with: the Japan 2011, Sumatra 2004, Chile in 1960, Alaska 1964, and this is the Chicxulub impact. We talked about, how they compare in terms of energy and um, energy magnitude and magnitude. And of course, there's again not that many of them because they're very high in magnitude. We talked about why you can't just relieve all the accumulated strain with just small earthquakes. This is basically the 100 years worth of seismic moment, and you can see just 3 earthquakes are basically half of the entire seismic moment released, and because they're so large in about 100 years, so 1906 to 2005. So we talked about that as well very extensively. Okay, let me go to the next lecture. Tsunamis, part two. So part one, remember it was the documentary, the wave that shook the world, where we talked about where tsunamis occur, very much around subduction zones for the most part, other locations as well, but mostly near subduction zones. Here you need to remember that let me point, oh, this is a bigger monitor. This is the wave crest, and it's like the top of the wave, and it's the maximum displacement there. And this is the trough. Yeah, right there is like the minimum, which is the slow point. And as the wave moves towards the shore, towards land, the seafloor will rise, like it becomes more shallow. And because of that, the bottom part will slow down compared to the upper part of the wave. And when this happens, the energy will get squeezed and it gets squeezed upwards instead of forwards because of this, the seafloor becoming shallower as it starts to, move more towards the shore. So because of that, as you see, the wavelength will shorten and the amplitude will increase because the energy gets concentrated. These are some important terms. Wave height, right? So this is the tsunami wave height. Uh, is basically the vertical measurement of a tsunami wave from normal sea level to the top of the wave. Run up is very important, is also very important. It's the maximum vertical height above the sea level reached by the tsunami water as it reaches this point inland, as it rushes the end point inland. Um, Next is inundation. We also talked about that. That's the horizontal distance. It's not a vertical distance. It's a horizontal distance that the tsunami water travels inland before in beyond the shoreline. We talked about the sources of tsunamis, landslides, whether terrestrial or underwater, volcanic eruptions, same thing. So Archimedes' principle, right? We talked about that. Physics is really fun. We talked about, this is happening in the Canary Islands. Um, Impact trigger, also meteorites can also cause that, like Chicxulub, right? Might have caused the extinction of dinosaurs. And then, of course, the subduction zones. We talked about, how this rebound, the plates get stuck with the under the subducting and overriding plate. And then once the earthquake occurs, there is this rebound in the overriding plate and it lifts a column of water because of that. Mm-hmm. We talked about those as well, where tsunamis happen, right, all over the world. Um, and we said that most of them actually, in the various parts that they happen around the globe, most of them happen due to an earthquake. Okay, we analyzed this in great detail. If you want, you can go back to the lecture. Tsunamigenic means that it can lead to a tsunami. Teletsunami is a tsunami that travels across like a long distance as well. These are some terms that I use to explain, so I thought I would just put them on a slide for you. And remember, it's important to understand what the trench is. So it's like this deep valley that forms when you have a subduction zone. We talked about how, this can, between events, you have this uplift with when the fault is locked or when the uh, interface is locked between the overriding plate and the subducting plate, and then you have subsidence once that's released. We talked about the largest tsunamis. You do not need to know these numbers, but do not need to memorize these numbers, but you need to know these earthquakes. Yeah, they'll also be in the study guide. So the Sumatra earthquakes, I showed you, how simulations of how the tsunami happened. We talked about that as well. 2011 Japan tsunami, and I highlighted, how I couldn't believe that these are actually cargo containers. I thought they were toys. There's just so many of them that there's just like significant damage. Uh, we talked about the Tohoku earthquake, especially in the context of the Fukushima Daiichi power plant disaster, how it survived the earthquake, but it did not survive the tsunami because the cooling system went down. They were they went underwater, um, and that caused the reactor to not, to melt down and not receive any cooling. And we talked about how today if you want, if you're interested, you can go to this website and monitor what's happening. The 1964 Alaska tsunami. I showed you some videos, and um, it was a magnitude 9.2 in the Prince William Sound. And we talked about the Alaska subduction zone in general. We also talked about Cascadia subduction zone, Juan de Fuca plate subducting under the North American plate, and how it caused a very large mega earthquake in the year 1700 in Cascadia, known as and it caused a tsunami in Japan that's known as the orphan tsunami because they observed the tsunami, but they didn't really feel any shaking. So the Cascadia subduction zone is similar in, extent to the Sumatra, the earthquake in Sumatra. And it's similar, and it would be similar. It's a kind of similar subduction zone to the one caused the 2004 Sumatra earthquake, magnitude 9 that we talked about, the Sumatra Andaman Islands that we discussed before, and that you watched the documentary about the wave that shook the world. So it would be around the same magnitude, around magnitude 9. We talked about evidence, the ghost forest, and the trees seem to have died, um, not over a long time, but really very quickly. So it's not like it was a gradual thing. It were covered by the tsunami water, which is salt water or salty water. It's not fresh water. And then you have, we talked about these sedimentary layers in Oregon Ghost Forest showing the tidal mud layer and then the sand deposited by the tsunami. We also talked about the orphan tsunami, right, in Japan. Um, there's a record of this tsunami happening in Japan without an earthquake. So it's because of the specific Northwest earthquake occurring on the Cascadia subduction zone. And finally, the tree rings, right? Scientists investigated the tree rings in the trunks of the ghost forest trees. They seem to have been alive, healthy until the late 1600s and dead by spring of the year 1700. So it looks like that the last big event in the Pacific Northwest was around January of the year 1700, and a similar size to the Sumatra earthquake. We also talked about the 1906 earthquake, and it was about 10 centimeters in amplitude, so it wasn't very large, but we did talk about it a little bit. We did talk about the Peru-Chile subduction zone and the largest earthquake that we have on record, which is the 1960 earthquake, magnitude 9.5. Next is volcanoes, right? Where are they located? Mostly around the Ring of Fire, really, and other locations, and sometimes even not near any plate boundaries. We talked about how they're formed, subduction zones, divergent plate boundaries are hotspots, and mantle plumes. These are the different types of volcanoes. We'll get to that. Near convergent boundaries, 75% of global volcanoes really are near the Ring of Fire. We talked about subduction zone volcanoes and how this, as the subducting plate flexes and dives, it releases some moisture and that lowers the melting point of the material in the overriding plate and causes this melting that eventually leads to volcanoes. Talked about the Alaska Aleutian Plate, Alaska Aleutian Subduction Zone, and especially the 1964 earthquake or site of the 1964 earthquake, and how we have this Aleutian Arc volcanoes that formed from due to the subduction. We talked about the Yakutat microplate and how um, it's a zone of high friction in here in Alaska. We talked about these are all the volcanoes in Alaska. We discussed them as well, and we talked about why we have these three main clusters of volcanoes, while we don't have any. We have the Denali volcanic gap. We don't have any um, volcanoes there, and it can be explained using the um, tomography that we discussed. You can see where there's this melt, and in areas where you find volcanoes, whereas in the Denali Volcanic Gap, for example, there is no such melt, and we talked about. Whereas in the Buzzard Creek Jumbo Dome volcanoes, you can also see some of this melt as well as in the Wrangell volcanic field, but you don't see it in the Denali Volcanic Gap. I walked you through some of the Crater Peak also, and the Wrangell volcanic field in Alaska, some of the Aleutian volcanoes. We talked about the Cascade volcanoes and in Cascadia, how they occur because of the subduction of the Juan de Fuca plate and, the dehydration that causes the volcanoes. We talked about how the Juan de Fuca plate developed, right? And now it's what remains of this ancient larger system. This is what remains now, the Juan de Fuca plate that's subducting underneath the North American plate. And I talk to you a little bit about the Cascade volcanoes. This is a nice slide that I like very much. Some of these are very famous, like the Mount Rainier, Mount Baker. Some of you also know about Crater Lake. So, uh, so it was very useful. We talked about how earthquakes can cause tsunamis, volcanoes can cause tsunamis, like we know, but tsunamis cannot cause volcanoes or earthquakes, and earthquakes and volcanoes also cause each other. We talked about the types of volcanoes. So, two main types, right? Composite and shield, kind of two main types. Um, Basic volcano plumbing. We talked about how you have this upwelling the magma, and you have a magma chamber, and then it starts to go out as lava. But the pressure drops. We talked about shield volcanoes, how the lava is mafic, so it spreads out, and it's not related to plate boundaries really. It's more like these hot spots in the mantle. Um, Talked about shield volcanoes, just showed you a video. It was a good video. I hope you can go back and review it. Hawaii, the Hawaiian Islands, this has been going on for over 60 million years. They've been forming and moving over the hot spot. Shield volcanoes, again, that's another example of shield volcanoes. Oh wow, we really we really covered this very thoroughly. And then composite volcanoes, um, these are some of the important ones. The lava is felsic. It's not as runny. It's more like uh, dense. And it usually forms over subduction zones, and they tend to be very explosive, and that's why they're very dangerous. This is from Mount Vesuvius. The hazards includes lava, pyroclastic, phreatic explosions, lahars, volcanic earthquakes, volcanic gases, tephra or ash. We already talked about tsunamis and landslides. We talked about a lava hazard. Lava is slow, so I mean, you can outrun lava sometimes, but a structure or a house or a school will not be able to. We talked about volcanic ash and how it's different from tephra, right? Tephra versus ash. Ash is a type of tephra that's very small, like less than 2 millimeters. So not all tephra is ash, but ash is tephra. We talked about how it's corrosive, it's dangerous, and how it's really it precipitates in a very, very high rates, and it buries everything very quickly. This is volcanic ashfall. The highest was the Mount Mazama in Oregon, 5,000 BC is the highest we know. Even Vesuvius was not that high in terms of um, the the amount of ash. And then we have Crater Lake. It's beautiful. If you I forgot to include a picture of it, but it's very beautiful. There's more ashfall in Montserrat in 1997. Then we have pyroclastic flows. These are extremely dangerous. They're very fast. They're hot clouds of similar to like tephra, but ash and ash. It's just very, very fast, and it's very hot, and it can I think 100 mile go up to 100 miles per hour. See how it very hot. See how it scorched this tree really. Talked about that. This is my favorite photo of all of them. These are two people just for scale. This is the kind of damage it did to the trees, the pyroclastic cloud. I showed you this documentary about Pompeii, how they got ample warning with all it erupted slowly in the beginning, and then there was a few earthquakes as well. Lahars, this is the hot or cold mixture of water and mud. Okay, it's just mud, ice and lava. So it can also be dangerous. It can bury structures. And of course, sometimes very unhealthy gases, let's say, come out of the vents. So that's another hazard. Phreatic explosions, they are caused by interaction of water with hot rock or magma. Also, they can be very dangerous. They're some of the hazards. The cascades are active and they might erupt and cause, several hazards related to volcanoes. And there are more hazards in Cascadia, of course. There is the hazard of a larger, even than magnitude 9, long earthquake. And there is the tsunami hazard as well there. All right, next lecture. Earthquake cycle recap. We already explained that. Just wanted to define some terms. So interseismic is this quiet period while strain is accumulating on a fault on a fault. Coseismic slip is the actual earthquake rupture. And then so this is the earthquake. It just quickly takes down the strain. And then post-seismic is the crust relaxing and setting after an earthquake. So that would be the post-seismic slip. We defined foreshocks as everything that all the shaking or earthquakes that come before the main shock, and then the aftershocks are after the main shock. And the main shock has to be the highest magnitude in that sequence. If it is followed by a, like for example in the Ridgecrest earthquake sequence case, that I told you about, we got a magnitude 6.4. We thought that was the main shock of the sequence, and then it was followed by 7.1. So now we upgraded that to be the main shock of the sequence. So it became the 7.1 instead of the 6.4. It has to be the highest magnitude. We did that in great detail. Showed you the aftershock forecast from the USGS, and it's not a prediction. It's just it just tells you the probabilities of different magnitudes occurring. We talked about forecasting and how it's based on really science, and it's really the best we can do. One of the best things we can do. The tectonic plates, they load the faults. We can measure fault motion using GPS. The slip on false creep can also be measured from GPS, and then earthquakes, they also, and earthquakes we can learn from past events, so we can scientifically we can quantify both or estimate both. But the thing is, we it's built on how the tectonic plates, they load the faults, and then you have this relief of stress from earthquakes or from creep. I did talk to you about some forecasts or some estimates of where you would expect shaking and how bad it can be, how high it can be, how high it can be. USURF 3 as well is a another rupture forecast that I talked to you about. Shows you, the likelihood of a magnitude, a 30-year likelihood of a magnitude larger than a 6.7 on each of the faults. Then we talked about the seismic gap, some of the famous seismic gaps or areas that have not had a great big earthquake, again, compared to relative to the size of that particular fault or particular, in this case, subduction zone, like the Shumagon Gap in Alaska. If you look, most of the Aleutian Arc ruptured in a great big earthquake in the past, but in the recent years, but not the Shumagon Gap. There are two more gaps that I also talked about, the Tehuantepec and Guerrero gaps in Mexico, some also gaps in Himalayas. We also discussed the similarity between the North Anatolian and the San Andreas Fault. They have like similar slip rates, age, length, and straightness, so they are comparable. And we know that most of the segments on the North Anatolian faults had ruptured and like a large magnitude large enough to be strain relieving. And we expected that next to rupture maybe was the Izmit section, which it did in 1999. But the issue now is that the section that hasn't ruptured, or in this case, the seismic gap, is really near Istanbul. And Istanbul residents need to be, because it's a very populous city as well. There's a lot of exposure there. So they need to be ready, get ready for, prepare for earthquakes, for, whether building codes or, in general resilience measures. And remember, it's not with the Turkey earthquakes, will be one of the case studies that are coming up, but that was not on the North Anatolian, it was on the East Anatolian fault. So it does not count. Does not count. We talked about the Parkfield gap as well, and how scientists were able to forecast that there will be an earthquake of about magnitude 6 in Parkfield within plus or minus 5 years of 1988 because of the fact that there was an earthquake there uh, almost in uniform-ish pure intervals. And they waited a long time. They drilled, the 3 kilometer deep San Andreas Fault Observatory at depth, or SAFOD, that we talked about, and they heavily instrumented the 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 SAFOD. We talked about all the different instruments there, and then the earthquake actually happened. It was late. And they did that, remember, because they wanted to capture any precursory signals as well. There, some people do think that there were precursory signal, but there's no consensus, let's say. But the earthquake did occur, and it was a magnitude 6, but it would, instead of occurring within 5 years of 1988, it happened on September 28th, 2004. This fault segment was correct. This is the shake map, some of the damage. We talked about some of the good things that we learned from the Parkfield experiment. We have so much data. We collected so much data, and we learned so much about earthquakes and about faults that it's like priceless amount of data from SAFOD. This is the part of the forecast that was released that year, 1988. And if you look, they had this. So chance of occurrence is the height of the bar, and then reliability increases. The color coded. If you look, this was 1989, so just 1 year after the forecast was released, and it didn't have very high probability or reliability, but it did happen. And so this, sometimes you have larger successes than other instances. But the Parkfield, they were very sure that it will occur around that time. Um, Hayward Fall did not have a great big earthquake since 1868. Talked about that, and therefore we expect that we have a strain relieving earthquake on it soon. We talked about, this is the history of it. We know that it's a creeping fault, right? We have evidence of creep. Already covered that before. Okay, so then I showed you this video to prepare for next lecture, which is the haywire scenario. So let's get to next lecture. In the haywire scenario, I spent a lot of time in that lecture going over numbers. No, I do not expect you to know the numbers, or to memorize the numbers. I expect you to know the numbers, but not to memorize them. Like to, understand, let's say, the numbers, like if they're high, they're low. So we talked about Bay Area hazard, the lessons learned from Kobe. I talked to you about my sources. This is the haywire scenario, a hypothetical magnitude 7 on the Hayward Fault with an epicenter in Oakland. So yeah, everything that we need to learn from that is to follow. This would be um, what the aftershocks and foreshocks would look like. Most of the damage would be from the main shock, but there will be a more damage due to in the aftermath due to the aftershocks. We talked about building damage, you know, uh, there's significant building damage definitely around the fault itself. Talked about, these are the impaired buildings. Again, very very much near Oakland, and near where the rupture will pass. Liquefaction, we have definitely very close to water, so there will be some significant liquefaction. We talked about that in detail. There will be landslides with probabilities that exceed around 32% on the steep slopes. So, um, these are landslide probabilities. So, yeah, near this is the Hayward Fault, and you can see that it's becomes red near the fault again. Um, yeah, these are very important to understand that these are some of the consequences of this kind of fault. We talked about, the services that we care about, water, gas, etc. Most water systems would be affected, with some East Bay Area residents losing service for up to 6 weeks or even 6 months. This is one of the important takeaways. This is with pipe replacement, so some measures to reduce issues, or reduce the hazard, um, increase, or reduce vulnerability. So increase resilience measures, or um, create resilience measures. And this is without current conditions. We talked about fire after earthquake, again, very close to the fault itself. That's more likely. We talked about impact over time, what happens short term immediately, how, people will start to move, how it will affect the population, the ripple effects over time. Um, how much, if you look here with the color codes, how much resilience, how much if we actually enact resilience measures, how this is with resilience measures, and you can see that the loss that the economies will sustain will be much less if we actually enact resilience measures. I also talked about that in detail. Okay, so and I showed you that video that you can go ahead and watch if you want to. Um, Next. So in lecture 13, we talked about earthquake prediction mostly, and early warning. We talked about how we have this significant hazard in New Madrid. Despite that, it's really not near any plate boundaries, right? New Madrid, Missouri, the New Madrid seismic zone. And we talked about these old earthquakes. Let me look at the larger diagram. It's the highlights. Um, we talked about these uh, really large earthquakes that occurred between the year 1811 and 1812, more than magnitude 8s. We, I showed you, we talked about how I showed you this map, and, these are the contours for shaking, how this caused the Mississippi to flow backwards, or that was temporarily, of course, or appeared to flow backwards due to the uplift and all the issues that occurred with the ground. And it was due to um, due to this, the real foot rift that lies beneath the Mississippi embayment. And it just, remember we talked about how that formed. It was supposed to the continent was supposed to break up, but it did not. And that was now a permanent weak zone, some intrusions, and causes stresses to concentrate, and these faults to reactivate. We talked about Dr. Iben Browning, who predicted an earthquake in Missouri in on December 3rd, 1990. And we talked about, how some of the local, unfortunately, some of the local scientists like Dr. David Stewart did not explain to people that this is not scientific, not based on on scientific, does not have scientific basis. And then there was this ad hoc workshop group releasing a statement about it, that the prediction, from it just does not have any scientific validity. But unfortunately, as we said in the lecture, it did not help much. And people started to panic. They were selling shirts about it. People were panicking. People were worried. They demanded schools to close. Shops sold out of supplies. We talked about that in great detail as well. And then nothing happened. The biggest impact was traffic jams caused by media vans leaving town. And the prediction was really made because of this planetary alignment that Dr. Iben Browning um, thought could be a reason for another earthquake. Uh, the last earthquake was 1811 in that area. So he predicted that with the planetary alignment and the gravitational pull they cause on the Earth will cause another earthquake. And the alignment occurs every 179 years. So 1811 plus 179, that would be 1990. But really nothing happened. And we talked about Earth tides and how they have more effect, um, how the moon and the sun have more effect on the earth than these planetary alignments. We talk about the impacts of a prediction. Their positive impact would definitely be to save lives, but there are some negative impacts like rescheduling of public events. It would cause population movement, financial issues, um, reduced availability of mortgages, change in investment patterns, decline in property values, decline in property tax revenues. Business activity will also be affected. We talked about some of the precursors, so those include P wave variations. You need to know the exact location of the earthquake to measure this change in velocity. And there is no convincing observations of this change. We talked about uh, this instance in Niigata, Japan, 1964, where there was gradual ground elevation and subsidence over decades, sudden subsidence near future epicenter in the year prior, uh, and then the um, the 1964 earthquake occurred, but really now we are not sure that this data was accurate. Palmdale Bulge, there was a bulge, and then it kind of started in around 35 centimeters, and nothing occurred. Radon gas, if it gets released, also can be a precursor for earthquakes, but there is no reliable data. Electrical conductivity, theoretically, is would change seismic velocity as well, but we don't have evidence that uh, we don't have reliable evidence that these signals are actually coming from the Earth because of a lot of man-made signals, like for example the BART, that electrical signals that are all over the place. The Oroville Dam. This is a successful prediction, case of prediction, uh, and this is due to earthquake swarms. So these are swarms of earthquakes. Earthquakes start to occur very frequently, low magnitude earthquakes, and then suddenly they are followed by a larger magnitude earthquake. So there are foreshocks basically. The Oroville Dam, the largest earth-filled dam in North America, filled in 1969, no earthquakes. June 1975, swarm of earthquakes. July 1975, swarm subsides. August 1st, magnitude 4.7 earthquake, followed by another minor earthquake. Bruce Bolt, the well-known geophysicist, he predicted that there will be another event or more events, and he was correct. There was a magnitude 5.7. Successful prediction in China, and then followed by a false alarm, and followed by a missed event. And we said the difference is false alarm. I tell you that there is a swarm. You evacuate, nothing happened. Missed event or missed alarm is I don't give you a warning and something happens. Animals, no evidence, no reliable evidence that animals. So yeah, some people say they hear the P wave, etc., but there is really no reliable evidence that animals can actually detect earthquakes. We
Uh,
talked about the successful earthquake early warning case in Japan for the 2021 earthquake in Tohoku. People were asked what they thought, and they received the alarm on the TV, on cell phones, different ways, email even. That was 2011, and 90% found it to be useful or unbalanced useful, and it caused them to take action and protective actions. Um, and mostly what they really important information that they wanted were expected intensity and warning time. We talked about the shake alert system of the West Coast. We will come back to shake alert. Why do we use earthquake early warning, public warning, first responder mobilization, healthcare like stop surgeries, utility infrastructure, for example, shut down power, mass transit systems, slow down trains, workplace safety, step away from heavy machinery and acids or something like that. So how does it work? We know that we get the P wave first because it's faster. Once an earthquake occurs, it goes to the earthquake alert center, and then the decision module will decide where to warn. And they have some thresholds for magnitudes and for shaking intensity, so they will warn certain areas and they won't warn others depending on their thresholds. What are the limitations of earthquake early warning? Proximity to faults. If you're very close to the fault, you will not get the alert in time. Data transmission latency, because we have the data will take some time to reach us, depending on what method we use to get the alerts. Inherent limitations. The larger the earthquake you want to be alerted for, the shorter the time. Like I told you, the earthquakes or the recordings of the earthquakes, they look the same in the beginning, right? In the first few seconds. You can't really tell how big the earthquake will become. So you can either get, for example, alerts for a very large shaking, in which case we will have to wait until we know that the earthquake will be large, and this means that we will lose some alert time. Or we can just warn you if the earthquake is small and you have to drop cover and hold on every time. But maybe that earthquake will just remain small and will never grow into a large earthquake. But we did warn you before that small shaking arrived. And then I think, yeah, this is, let me go to, because this is what I added to a lecture, the last lecture. 14. This is the last part of the lecture. Hmm. Okay. So applications, personal safety, move to a safe zone, automated control, slowing, stopping, isolating sensitive systems, Situation awareness, initiating response before shaking. Uh, these are accounts from people who found the shaking, the early warning, useful and were able to use it to get to safety. Um, So the first thing is being mentally prepared for shaking when you get the alert. So for your personal safety, protection from falling bookshelves, etc. Um, Staying away from masonry and falling hazards. Second is automated control. And we said the important thing is that it's automated. There, you don't need to wait for a human to initiate these actions. So the the system will get the alert and initiate those protective actions immediately. We talked about this chip manufacturer. They spent some money. They had lost a lot of money and a lot of production days. In a couple of previous earthquakes, they invested in an earthquake early warning, in a system that would initiate actions after earthquake early warning, and they were able to save a lot of money with that. Also, slowing of trains that they don't derail. Even during the magnitude 9 Tohoku the trains stopped or slowed down and did not derail. The BART is a subscriber to the shake alert system, and the shaking increases beyond magnitude 4. The trains will slow down from 70 miles per hour to 27 miles per hour pretty quickly. Um, we talked about, you know, t telling planes to go around, tell pilots not to land planes because there's an earthquake going on. Isolating hazardous chemicals and machinery, like I said, putting sensitive equipment to stable state, stopping elevators. That's important. Never go into an elevator, remember? Never go into an elevator during an earthquake, and opening doors at the next floors. Smart buildings can also initiate protective actions, situational awareness, understanding why systems are failing, rerouting power or communications, preventing cascading failures because of that, initiating emergency response. Like for example, also dispatching firefighters and um, having them maybe go ahead and head to areas that will be hit hard by the earthquakes or before communications break down. There's another, I took you to the Shake Alert website in this lecture, and I showed you how you can get your different what are different ways to get your alert. So you can get it through My Shake app if you download it. If you have Android, you can get the Google alerts, or you can get the WIA, the wireless emergency alerts, on your phone uh, to alert you for the Shake Alert. We also talked about the Shakeout annual training or annual earthquake drill. That earthquake drill that a lot of millions of people really participate in. Um, okay, thank you very much. I will share the slides. I just got very tired. I'm going to share my I'm going to share the recording to this lecture and as soon as possible. Let me know if you have any questions. I will update the um, the study guide accordingly if you want me to. All right. Good luck. Let me know if you have any questions.